For this project, our group focused on using neural network to make financial market prediction. The motivation is very simple. Traditionally, it will take a professional years of experience to develop a sense of understanding for the financial market. A neural network can finish the same amount of training just within hours. And we want to see if we can truly develop a neural network to make the prediction, and we want to all compare the performance between different neural network structures. We pull our data from Yahoo Finance, which contains daily stock price information of 5 different features. We then split our dataset into 3 different parts: a train set, a validation set, and a test set. We choose our baseline model to be an LSTM model and use zero change prediction model to modify the error we get to give us a more intuitive result. We first run a simple training and testing on different time range of datasets, and we're surprised to find that despite the fact that neural networks should be able to use large datasets to achieve better performance, our model actually achieved better performance on a smaller dataset. And that's because we believe the financial market is an evolving market. Therefore, we should not make a future prediction using a model that was heavily trained on ancient historical data that makes it less focused on the current data. As a result, in order to correctly evaluate the performance of our model, we should choose the time range of our dataset correctly. After choose our dataset, we optimize our structure for the LSTM model. And again, we are surprised to find that a simple version of LSTM actually achieved the best performance here. And we think that's because due to the simplicity of our dataset, with only 1,600 data points as well as only 5 features, a more complicated version of model can overfit on the training set and cause larger error on the test set. After we have constructed the baseline model, we implement 3 different other models and compare the result with the baseline. First, we implement our GRU model, which is a simplified version of LSTM with one less hidden state and use less parameter to train and fit the model. It is widely believed that a GRU model can actually achieve the similar performance compared to an LSTM model on some tasks, but also requires less time for training. Our result indicate that it's true that GRU is more efficient on time, but it have to sacrifice a lot on training error for the topic we choose. Therefore, it is not an optimized choice. For the next part, we apply the attention module onto our baseline LSTM model to see if we can increase its performance. Attention module will help the decoder of our model, which in this is a linear layer, to focus more correctly on the information that's generated by the encoder, an LSTM layer. In theory, it should maximize the usage of correct information and increase the performance. But our results indicate our model is severely underfit for both the training set and the test set. And we believe that's because due to the time limit, we did not find the optimal solution for the attention structure. And we believe with the correct structure, the performance can be increased significantly. Lastly, we implement a simpler version of transformer model. A transformer neural network is designed to process a sequence of data with additional attention module, just like an LSTM or a recurrent neural network with an attention module. But unlike a recurrent neural network, it does not take sequencing input one at a time. It takes sequencing input as a whole, embedded with a positional encoder. We implement a simpler version of transformer by replacing its decoder with a simple version of one layer linear layer. And that's because we believe the transformer model is complicated enough already, and we don't want to give it too much degree of freedom that will cause it overfit on our data sample. The results indicate that even though the test loss of the transformer model is slightly higher than the LSTM model, we can actually see the performance. We can actually see the prediction from the transformer model being more volatile rather than the smooth prediction from the LSTM model. And that's an indicator that our transformer model is overfit on the data that it starts to simulate noise on the test set. We validated that by temporarily increase our dataset, both on the time range and as well as add more noisy feature to create larger volume. And at this new dataset, in LSM prediction, the performance has been decreased, while the transformer prediction has kept relatively the same and even increased a little bit. And that fits our analyze pretty well.